So I think I have 3 goals today. One is to to talk about flow cut gap. I want to finish the proof saying that the flow cut gap is at most log n, or actually at most log NA, where NA is like the support of the A node weighting. Okay. Next is I just actually want to mention that this is tight. You cannot improve this, and like there is an easy example to see this. And mention quickly about directed version, which is a really interesting topic, still wide open. Okay. And then I would, if I have time, I talk about LDD, the thing in the homework. If not, then you just solve it yourself. It's okay, because yeah, the lecture note that I gave is kind of nice and like it's really nicely written. Yeah, it's by Anupam Gupta, who is now at NYU. Like if you have anything talked by Gupta, by Anupam, then watch it. Every of his talk is one of the best. All of his lecture notes are great. Yeah. Okay. So what we did last time, right? Like I tried to prove this, that if the node weighting is cut expanding, then it's also flow expanding up to log n factor. And how do we prove this? We just assume that the product demand takes a lot of congestion to route. Then we try to find a sparse cut. Find an S such that the cut size is something like 5 times log n times the volume of A. Yeah. Okay, so that's the strategy. And I'm just gonna skip stuff. And then so far, okay. Let me recall very quickly still. What we did is we solved the LP and see that like we solved the LP that capture that I'm just gonna close this. If the congestion of the best congestion to route the product demand is big, then by looking at the dual LP, then we're gonna get this length function L such that the total length is 1 and the distance between all pairs are kind of spread out. Yeah, that's how you should think about it. Like they spread out a lot. Yeah. Okay. And what we do is just we look at this graph, think of L, like look at the graph G, where you think of where L is like a length function. And then compute low diameter decomposition on this graph, right? And we look at 2 cases. If when you compute the low diameter decomposition, if it's kind of look like this, where there are many components, each of the component is not too big. So each of all components, after you cut all components in the low diameter decomposition is not too big, then just greedily collect the cluster until the size of S is kind of balanced. Just return that and you're done. Otherwise, if it's not in a balanced case, there's like kind of one cluster that contains a lot of A. And then we're gonna do some sweep cut from here. Okay. And so what we do, we do this, right? We take the component k to be the big component that contains a lot of a, and then we sort vertices according to the distance to k. Okay, so k is a big component, and then we look at, like, for each node, look at its distance to some node in k. So that's, we define that as pi v. So that's like a number for each node. Once you have this number for each node, you can sort it. So like now, like vertices are sorted in a line, right? And now like you can define a prefix cut, which is like Si is like a Vi up, V1 up to Vi. So S1 is here, S2 is here, S3, S4, S5, up to Si. And there can be up to Sn. Sn minus 1. Yeah. Okay. Okay. And we're just gonna, like, among all this level cut, we just return the best cut. Okay. So we just need to analyze, like, I want to say that one of the value here among all choice of k, one of them will be small, something like 12 phi of order phi. Okay, so we analyze it a bit, and yeah.
How do we know there are vertices outside of the heavy component?
How do we know this?
Yeah, like how do we know?
Good.
Like the heavy components just.
That's a really good question, actually. Suppose that it's not, then you can actually say that. Actually, that's a good point. You can actually say that the congestion need to be small. So as in.
Because.
So you kind of know that every vertices are kind of spread out. So I don't give the formal proof right now. You know that vertices are really spread out. And then the diameter here is tiny. So if every node is within this tiny distance, actually let's do it formally. So, but this is a great point. I didn't show it. Okay, let's see why. Suppose that all vertices are in K, right? Somewhat one component. Okay, so basically this UV is at most this much for all UV. Okay. At most 1/4πA. Okay. So everything is so close together, but at the same time we know that things are spread out. So that should give you contradiction already. So let's just compute it, calculate it. So this implies that sum DUV, right? This is at most what? This thing is just some constant here times this times DUV summing over all U. What is this thing?
A.
This is just A. Like the total demand when you sum overall product demand is just A.
That's because D
Respect A.
Respects A, right?
Yeah. So this is less than 4/5. So that contradicts with this thing. So it just cannot be the case that this cannot happen. Good point. Yeah, I should have added. Yeah. But so Okay. So good. So back to our business. We know that K doesn't contain everything. Yeah. And so at least like this number is non-zero on some node. Okay. And then we just do this sweep cut and return the best one. And we're gonna analyze this. And we analyze it up to some point, right? We have shown that, we look at this thing, the mean overall K of this, okay? And we analyze it up to this point, that this thing is gonna be at most this sum. I want to repeat this. Okay? And we also have shown that this numerator is at most 1. Okay? So why is that? Why is that? Well, should I repeat it or I don't? Or should I? No. Okay. I skip. Okay. Because we show this. Okay. Let's lower bound this thing. Yeah. So this is going to be at most 1. This is going to be at least 1/12 phi. If we have shown this, then we are done. Okay, let's prove this. Okay. So, okay. Right, here you go. Okay. So we're gonna analyze this term, right? Okay. So let's simplify things a bit. Well, we know that. Let's look at this one. It's kind of measure like how far away U and V is in terms of pi. Okay, but there are actually many nodes in K whose pi value is just 0. Yeah.
I was just gonna ask, the definition of pi of V is the distance from the node V to the component K, or
Yeah.
like the shortest?
Yeah, the shortest length, the shortest path, the length of the shortest path from V to some node in
Something.
K. Yeah, to some node in K.
In K.
Yeah, yeah. Right. So, okay. We analyze this. There are many guys in K here. Everyone in K has value 0, right? So let me just try, let's say that I just analyze the pair between a node U in V and a node V in K. Let's do that. Yeah, okay. So in that case, if we just restrict V to the guy in K, then this is 0, right? So this is just gonna be pi of U only. And then we just sum over degree, like sum over D from U to V, sum over, like, and you sum over all guys in K. So this become duk. This is just the definition. Like this is just a sum over D, V, and V in K. Right? Are we good here? Yeah. Question?
Doesn't the sum over UV also consider demands between UV that aren't in K?
Yeah, but I'm trying to lower bound it.
Oh.
So I just try to sum over like a smaller number of set. Yeah. Okay. Okay, we are up to here. And now like this guy is gonna be at least AU over 1/3. Okay. So
Does the 1/3 come from like the heavy case?
Exactly. And like, this is where we really like don't just say that this is where I don't just say that D respect A, but I really use the fact that D is a product demand. Okay, because if D respect A, it's kind of just give upper bound on D, but here I kind of want to lower bound D in terms of A. Okay, and let's see, like I just proved that this thing is at least this thing, right? Let's see the definition. Like DUK is just like a D summing over all node in K. This is just the definition. Now, like the definition of DUV is like AU times AB over size of A. That's the definition of product. And now, like but now, like this sum over all V is just AK over A. But K is big. This is like at least 1/3. So up to now, I proved that like to lower bound this thing, I just need to lower bound this thing. Okay. Which is like summing over all node, the mass, the node weighting of U, and the distance from U to K. Okay. Okay. So up to this point, you should get some intuition that this should be big. Why is that? Like, you know that things are spread out. Like UV, they are, if you sum over everything, they are spread out, right? And like, but okay, and now like you know that everyone in K is just so close to each other. Everything in K is so close to each other, and so there must be some guy that at least like kind of far away. That is, so there must be should exist some node such that the distance from V to K is big. Because everything here is so close to each other, but overall things are spread out. so there must be some node that is far away from K. Is this intuition kind of with you? Yeah.
Also, K is big, like the size of K, but everything in K is still within that like delta diameter within each other, right?
K is big in mass.
In mass.
But it's so close to each other. It's like really dense, yeah.
Why is everything else spread out? So
Because we know that a sum of this thing, this is big. This is an assumption that we have. This is what it means by like spread out. Yeah. We know that like this thing, like L is at most 1. So the length is not too big really, but the total distance between things are kind of big. So like this is just numbers, but this is the intuition is very important. Yeah. Okay. So now you should know that like this is big. Let's formalize this. Okay. Okay. So, okay, to formalize this, I will use like the fact that first thing is spread out. Like this is an assumption that we know, right? From the dual, like we know that this sum is big. Okay. And now use triangle inequality. Right? The distance from U to V is at most the distance from U to some guy in K plus the diameter of K plus distance from V to K. Okay. This thing is this path, and this thing is this and this, and this thing is this thing. Okay. So if you want to go from U to V, you could go this way too, but it's at least worse. It's worse, yeah. So you have this thing, okay. And now just kind of rearrange, like just do manipulation. What is this? This is just pi. Yeah. Pi u, pi v, right? Okay. And this is something small. By small, I mean something like 4. Yeah. Okay. So this sum multiplied by this thing gives you this part. And this sum multiplied by with this one gives you one term here, right? It's just like this multiplied by this summing over all v. It's just like a of u.
Because pi of any v is 0. Is that what I've heard?
Pi no.
For any v belonging to k. Or...
No. What I'm doing here is just let's look at this term. Right. This is a sum duv pi u summing over all u and v. So let me instead kind of take two sum, separate the two sum. Okay. This sum over v is just au because
demand is a respecting. Right?
Yeah, this not just a respecting. This is the product demand. The product demand, like if it is a respecting, you only know that this is at most au, but it is exactly au, right? Because if you have d here, in product demand, you have equality here. Yeah.
Like here, it seems like inequality would be sufficient, right? Just to boost AU.
You are right. You're right. Yeah. I don't need equality.
So we could also use the fact because d is a respecting.
Yeah, exactly. Good. Yeah. Okay, so I just need this. Yeah. Thanks. Good. So just by this calculation, we get one term here. And when we do the same thing for v, but now summing over all u, just get the same thing, but now instead of it's sum over all u and the same thing summing over all v. So this is just the same thing. So I have factor 2 here. Right. What's this? This is just a constant. What's this? Can we upper bound this thing? Can you simplify this? Yeah, it's just A. D is A respecting, so actually like 2A. Yeah.
So that term just, if we continue the inequality, the second term would just be 1 over 4/5, or
Which one? Sorry.
the second sum, this one,
This one?
the one below. This is, I mean, this can be like upper bounded by A, right? So
Yeah.
then the second term is just can be upper bounded by 1/4 pi or
Almost. Because this is at most 2a, not just a.
but why 2?
Because actually you're right. Just a, yeah. Yeah, just a, yeah. Right. I think. Yeah, at most a. So this is at most, this whole thing is this whole thing then at most 1/4 phi. Okay. Somehow I just think that is 2a, but yeah, doesn't matter, yeah. So now you can lower bound this thing, right? Because you can move this to subtract from here, and now you'll get the lower of this. So what do we mean? Like, okay. So I thought that this is 2a, so okay. Anyway, so now it implies that 2 of this thing is at least 1/5 minus 1/4 phi. So this thing is at least 3/8 phi. Are we good? So we are done.
But I thought we needed to do 12, or it was somehow upper
Yeah,
bounded
this
by-
is better than 1/12 phi.
I'm just wondering, where did the 12 come from?
It is from my bad calculation. I thought that this is 2a.
Oh, I see.
Yeah, it's some constant. Yeah, 12. Yeah. Yeah, where is 12? Even if
Don't we get 12 from the previous part? Oh, we had like a.
there is 3. Yeah, there is factor 3 here too. So actually, right now we have that. This is at least now like
1/8 or
times this thing, which is at least, yeah. So if you use the bad calculation that I oh sorry, if you use the bad calculation that I had, like I get a bit worse thing here. It's gonna be 12, but yeah. Okay, so we're good. Yeah. Even better bound. Yeah. Okay, so far we are done. Any question? This basically show you that in the heavy component case, we get this. So it means that in this case, we don't even pay log n, right? We get even like sparser cut. Yeah. So that's great. Yeah. It's only in the balance case that we pay log n. And note that like, so you see that like this flow cut gap here, the gap, the log n is just really from this factor. It's really from when you apply low diameter decomposition, and there is log factor here. That's where you get log n from. And now that, yeah.
Oh wait, sorry, but in like the first case, we weren't using the fact that the decomposition is low diameter. I guess like is the like log factor coming from some property of the decomposition other than the low diameterness?
Say again, sorry. Repeat that.
So we're getting the log from like the first case.
Yeah,
right?
the balance case.
The balance case,
Yeah.
yeah. But in the balanced case, we don't require that the decomposition has low diameter, right?
No, yeah,
Okay.
no.
So, I mean, is it some other property of the decomposition that requires the log there?
Like, so I want this decomposition to have low diameter because in the heavy case, we need it.
Right.
And in the balance case, we only use this part. But it's like, okay, like this is used in heavy case, this is used in balance case, but to make everything works, I need two things at the same time, right? I need this decomposition at the same time.
Okay.
I'm not sure I answer your
Yeah, no, it's good.
Okay. Okay. So the point that I want to make is this. You're gonna see soon that in some graph you cannot beat log n. But log n really just come from this thing. And there are special graph like that is natural, like planar graph, many other kind of graph, like a minor free graph and so on, where you don't need to pay log n. Yeah, this is just a constant. And then you get immediately that a flow cut gap in that class graph, in that special class graph, is just a constant.
But in general, for like,
In general graph,
it's like the support of it, or
yeah,
or
in general
the
it's
log-
support. It's always support of A, yeah. But for some special class of graph, this is even like independent from everything. It's just a constant. Yeah. Like planar graph that people care a lot about, and many special class of graph that people care about. This is just a constant. Yeah. Okay. But throughout the whole course, I kind of just care about general graph. Yeah. Okay. Okay. So that's the important thing that I want to make. Like many graph classes admit LDD with constant overhead factor. It implies that flow cut gap there at most constant there. Okay. So this is kind of nice, and people use it. Yeah. Okay, so question before I go to the next thing. Yeah.
Is there, just curious, some graph where the flow cut gap is exactly 1, so that it's
A
kind of
tree.
a tree?
Tree, yeah. You can try to verify that, yeah. Yeah. Yeah, for example, trees, yeah. Planar graph, bounded tree width graph. Minor free graph. Yeah, okay. Okay, good. So let's see the lower bound. Yeah. So you you cannot hope to get this lower than log n. Let's see. So the low bound is the how to prove lower bound. What I need to show you is that there exists a graph such that maybe G such that G is the constant cut expanding is a constant cut expander. but G is like the product demand, yeah, like a product this G product demand requires at least log n congestion. Everyone agree that if we show this, then we are done, because it has really big cut expansion, like constant, but this thing just means that the flow expansion need to be less than 1/log. This is just kind of, yeah. Okay. So, question about this? So now the proof is that let's take G to be a random graph where, yeah, let's say, so the point is that you can construct, yeah, let's say that there exists G which is like a constant cut expander with max degree call it delta to be a constant. There exists this thing. Why a random graph would do, and you can try to prove it. Not just some random graph. Like if you really just take random graph where like the expected degree is a constant, then it might not be even connected. But let's say you like a random 3 regular graph would do, or like if you take like a union of 3 random perfect matching. So I mean like you have a graph with let's say 2 n nodes and just match them perfectly in random way and repeat this 3 times. That would give you this. I will not prove this, but this thing exists, okay? And it's easy to construct it. Okay. So the point is, I just want to like there exists this thing with low degree. Okay. Yep.
If it's random, then do you mean like for all like it's always going to be like omega 1 cut expander, or like
Say again.
if it's like random, then is it possible for it to not be like if it's like randomly generated?
It's gonna be cut expanded with high probability. Yeah. Yeah. So like if you generate in this way, you're gonna get that is cut expander with some probability, and actually with high probability. Okay. And now, I won't go into this, but let's say that now we fix this graph. Okay. So let's look at the product demand. Okay. Second, we know that I want to claim that, okay, let me give you intuition. Yeah. most of the pairs in G cannot be too close to each other. So most pairs UV would have distance, like most pair UV, the distance in G is at least log n, or like log n over 10 or something. So why is that? Well, if you look at some node U, what's the number of node on the first like radius of length 1? This is at most delta. Next level, delta square. Next level, delta cube, and so on. Right? But this is like a constant. How many times, even after I let's say that now this is like a of length log n over 100. The number of nodes here is still at most to the log n over 100, which is still like less than what? Less than something like root n. Yeah. If delta, think of delta as 10 maybe, yeah.
Delta is some constant, right?
Some small constant, yeah. Right. So if delta is 10, then this is tiny, like small. So like most of the guys are far away from you. From every perspective of every node U, most people are just far away from me. Okay. Okay. So now, okay. So now, suppose that maybe I even say that like, let's say I want to do matching demand. Yeah. Like, good. Let's say I just, there exists a degree respecting demand. Okay. So now consider a matching demand, a perfect matching demand. So what do I mean by perfect matching? Well, like kind of quite intuitive. I just kind of match nodes in this way. And I want to send one unit here. Okay. But I try to match only between the guys that are far away from each other. So I choose U and B such that the distance from U to B is big. It's like log n. Okay. Between like pair of distance at least log n over 100. So what do you know here? You know that if you want to route this like between each of these pair, you would need to consume something like log n congestion. Like it need to go through log n many edges. Okay. So the total unit of congestion that you consume throughout this is like n log n. Like let's think like I just compute the total capacity that all this flow go through is at least n log n. But what's the total capacity in G? is at most like n times degree. It's around order of n. The total capacity is linear in n, but you know that the flow need to consume like n log n capacity. So some edge need to have congestion log n. That's it. Make sense? Good. Right. Question about this? Okay. All right. So and know that like so this gap come from expander, but like in many of the graph that I mentioned, like trees, low bounded tree with minor free graph, planar graph, expander cannot exist there. So so that's why like you can hope to get constant, but here you get this thing. All right. Okay.